So let's get into what we're going to talk about, and we're going to talk about Lab 3. So welcome to week 5 online Lab 3 lesson, and we're going to go over some really amazing stuff, and I'm going to show you some great videos. So I'm going to do like kind of an overview of what we're going to do, and then we'll dive in and look at it. So let me show you. Let me share my screen. So we're jumping into Blackboard, and here we go. So we're going to go down to week 3. Here we are in week 3, and welcome to week 3. So right now what's going on is that, oh no, is this, I'm gonna go for, here we go, that's better. So I'm in group A. So here, okay, so welcome to week 3. And what's going on here is that we're gonna be talking about, I've got some really cool stuff going on. I've got a discussion, which is a PDF here, that is a whole PowerPoint that I made. And we're actually gonna go through this PowerPoint. That's what we're gonna do today. And the other thing that we're gonna do is we'll actually look at Lab 3. And then I want to introduce to you guys these videos, which are going to help you tremendously. I really need you to watch these videos. It's really going to be very empowering. And they're nice and short. This is 7 minutes, and this is almost 6 minutes. So it's really good. So what we're going to do is let's actually take a look at Lab 3. So we've got two things going on. We've got the actual lab itself, and I'm just assuming that you guys all understand. I need you guys to understand. I'm hoping you fully get it, that all of the work you do in the lab, you have to write all of the answers on the computer. You do not have to physically write anything down on paper. And if you do write it down on paper, that's fine, but don't hand that paper to anyone. And all of your work is completely on the computer. So I think everybody gets that, but I just had to say that again. Okay, good. So yeah, and if you're not actually entering the work onto your computer, you won't get any marks. Except for some of you in Lab 1, which was a weird thing, and I still haven't figured out how to fix that. So let's just stop talking about that and get back to the work that I wanted to do. So this is the lab itself. Now this is what I do to make these, is I actually just take screenshots of, it's actually a quiz. The lab is actually a quiz, but I take screenshots of the lab quiz, and then I just make it a PowerPoint document. So we will go over this, and this is your experience going into the lab. But what I want to do first is I actually want to jump into here and talk about this PowerPoint that I made, which is a great PowerPoint. All right, so welcome to the PowerPoint that we're going to talk about Lab 3. So I'm going to talk about relays. So you guys already know about ladder logic to some degree because you've already done some ladder logic, but I want to talk about relays. So we're going to talk about like the operational principles of a relay, and we're going to become familiar with the use of relays to control devices. A device is like something that goes, right? And familiar with inputs and their configurations, whatever an input is, but that's an interesting concept. There are these devices, which are actually outputs, and inputs, which are like signals that come in. So we're talking about logic here. So that's why we actually call the ladder logic, right? So we're going to gain an understanding of contacts and this whole thing, contact and contact terminology. So it's important that we understand how to talk about contacts. And then we're going to unpack logic statements in ladder diagrams. And today, it's a big deal. I'm going to introduce you to the concept of not. So you guys are good with and ors because you did that in Lab 2. Lab 2 is all about ors and ands. Now we're actually going to do nots, which is pretty cool. We can't do nots without a relay. So let's actually talk about what a relay is. A relay is an electromechanical device. It's a really cool thing. And you guys know what an electromagnet is. You take a core of iron core and you wrap a wire around it, and then you have an electromagnet. So if you turn the electromagnet on, it's going to change the contact in a switch. So as you can see, this is a single pole double throw switch. Up, down, up, down, up, down. So normally, because the concept of normally is this thing with this spring. So if a switch has a spring in it, it has a normal state. So normally, this is the common and this is the normally closed. Because normally, this point right here is closed. So if I were to connect this green wire over to here, then this light would actually come on without me energizing the coil. So if I energize this coil, this blue line moves and goes down to here. So what we do is we call this a normally open and this a normally closed. So the name of this contact is a normally closed. The name of this contact is a normally open because normally it's open. and normally this is closed. So the spring creates the normal state. The active state happens when I energize this coil and I close this switch. So this is cool. Get this. I can use a switch that runs on maybe low voltage to control high voltage, and that this may be like a 100-volt battery, and this could be a 100-volt bulb, and actually could be a lot of current going through here. And this little switch could be like a little tiny micro switch, just running a few milliamps going through here, making a coil make this thing move. So this whole spring here, this throw goes down here with the electromagnet. So I'm actually controlling really high current with low voltage and low current. For instance, a doorbell. I could actually use a doorbell to actually control something that was really high current and high voltage. So that's what's going on. And the first relays were used in telegraph circuits. So what they were doing was they were sending these signals along these long, long lines, and they needed a lot of power. So, but the little button that you pressed on with the telegraph, it was beep, 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 that little tiny button, you can't put a lot of current through that. So what they were doing was they were putting a small amount of voltage through that little button, and that was controlling a much larger relay that would send a much stronger current and voltage down the lines. It would go really a far distance. So what's going on is that you can easily identify the green. So we talked about this. I just kind of unpacked what this is. That's the coil itself, and this is the switch that's inside. And when we energize this coil, and that's the word we use, energize the coil by just closing this switch, this magnet becomes energized and it pulls this down. So that goes down and it connects to here. So all of a sudden the light comes on. When I turn the switch off, because there's a spring there, it goes back to its normal state and this becomes closed. But there's nothing hooked up to here. So it's okay, nothing happens. Just the light turns off and that's it. So let's take a look at an example. No, so there are applications. You have to take a look at applications, and I have a really cool example. So I want to talk about a few standard concepts. There are a lot of really cool things we can do with relays. Like, it's amazing. But relays can be used to control high voltages with low voltage, right? So essentially, I could have a doorbell that actually in my house, maybe some really big, huge doorbell where there was like this big bell that went gong, gong, really, banging. Whatever that is, it would take a lot of power to run something. I maybe need really high voltage and high current with some big motor that makes this thing move. Well, I can't run all that through a doorbell. So I use the doorbell to run this coil. And then this coil is going to change the contact here, and a lot of current can go through here, and then this would be my big motor that runs some big bell or something. So that's what's going on. So relay is just amazing. So let's just take a look at that. Now, you know what? This is a whole example here. You can read this later, but I'm just going to tell you the story. Okay, now I'm going to tell you a story. Okay, this is the story. Now, you are you're the manager of a plant. Okay, so there's this big manufacturing facility, and you're up, in your office, and you're looking over the floor, right? And you've got this switch on your desk. It's just a small switch, just a little toggle switch. It doesn't actually need to be really big, but you have this little switch, and that switch can actually turn a ventilation system on way on the other side of the factory. Because you see, maybe as you're looking out over the factory floor, you're like, there's too much dust in the air, or maybe a little bit of smoke in the air from some of the machines, or the guy's welding in the corner, and there's just some smoke there. And you're like, I want to turn the ventilation fan on. Now, we're talking a big factory, so we're talking a really large ventilation fan. It's a big honking motor. It's like this. It runs on 220 volts, and it runs like 30 amps. So you've got a switch on your desk. Meanwhile, the actual motor's on the other side of the factory. It's like 100 meters away. So if you wanted to, you could run a wire from the motor all the way along the shop floor, or you'd have to go up to the ceiling, along the ceiling, and then down into your office, and then along the floor or in some conduit down onto your desk, and you could put a switch on your desk. Now, that wire would have to be able to handle 120 volts with like 30 amps. Here's a big motor. So that wire itself is going to have a lot of safety protocols just to run it. You're going to need a special conduit. You're going to have to actually deal with really heavy wire as well, because it's to have a wire going like 100 feet, 100 meters this way and 100 meters back that way again, that's going to have 20, 30 amps going through it. You're going to need a really like as thick as my finger. That's going to cost you thousands of dollars. Plus, the switch that's on your desk is going to be like really big, like a really big switch. Plus, you're going to have this switch on your desk that has a potential of 220 volts. And if you spill your coffee on it, yeah, or whatever, you want that thing sitting on your desk? No. So the solution is to put a small switch on your desk and run a very small wire that goes all the way back, so 2 wires obviously, that go all the way down to the, because you need current coming in and then going back again. So all the way down to the ventilation shed or to the motor that's way over there. And that wire that you have to run can actually be just 24 volts. And it's not a high current wire. So because it's 24 volts, a low current wire, you don't need to go through a bunch of different safety protocols and put it in a conduit and have a really heavy gauge wire. You could run that wire for probably $100, having some guy just install it with tie straps along some pipes. Really, I mean, it's 24 volts, doesn't really matter. If you wanted to install just a heavy cable from that motor all the way to your office, it would cost you thousands of dollars, because all of the safety protocols and the heavy wire, the voltage, you have to have a special enclosure on your desk to handle that actual heavy current and voltage. So now you've just got like a small switch. You could even probably use a doorbell. And it's just a small little toggle switch. And when you toggle it, what it does is it talks to a relay. And the relay is actually beside the motor. That relay has these contacts in it. And the contacts are big, heavy contacts, and they can come up and down and up and down. And the thing that's pulling those contacts up and down is an electromagnet. And you're running that electromagnet from the little switch on your desk. That's an amazing thing. So we can have this small voltage of 24 volts running a coil, and it's actually changing the contacts. It's like it's just controlling the switch that's actually in that generator room, or I mean the ventilation room. And that switch is then turning the fan on or off. So relays can do that. They can also do a lot of other cool things. The other thing we can do with a relay is we can reverse logic. Because remember with that picture, I showed you that there was a normally closed contact and a normally open contact. So what we can do is, if we were to actually hook up that lamp to the normally closed contact, and we were not to turn the relay on, then the light would be on. So if I don't turn the relay on, then the lamp comes on. It's really weird. So if not relay, then lamp. So we're kind of reversing the logic, and that's what a not is. So when we reverse logic, we say not. So I could say, if it was just straight, I could say if switch, then light. I think that makes sense. So if switch, then light. I think that's, pretty normal. But now I could say if switch, then not light. Watch this. If I go over and share that again, now this is kind of, just bear with me while I jump back and forth over here. Okay, so here we go. Let me go back up here. So in this case, we can see that if I close this, this light will come on, because this will move down to here. This arm will move down to here, and the current will flow through here, and it will flow out of the normally open, and it will go to the light. So the statement here is if switch, then light. Now watch this. If I were to connect this light over to here instead, and I close this, what happens is this armature moves down to here. So this arm moves down to here, and now because the light's not connected to this, the light's off. So I can say if switch, then not light. Yeah, I can reverse logic. So relays can reverse logic. We can save a lot of money because we can kind of remote control things. We can control something way on the other side of the factory that runs on very high voltage with just a small switch. It's really cool. We could use a 12-volt relay at the motor to activate the motor. So in the contacts on the relay, they can handle the actual contacts. These things here, we call them contacts. Right in here, we call that a contact. They can handle a lot of current. So what's going on is that they can actually run that huge motor. Well, all I'm doing is I'm running a 12-volt coil with a small switch, and that's just sitting on my desk. It's pretty awesome. So we can control low voltages with high voltage. We can reverse logic with them. And we can also, if we wanted, we can control high current with low current, which we're kind of doing with that example with the switch on my desk, because the actual motor is running with high current and the motor is also running with high voltage. So I can use low voltage to control high voltage. I can use low current to control high current. And we can actually do something called a memory latch, which we will talk about next week. If you come to whatever, in Lab 4, we're going to do memory latches. Lab 4 is going to be all about memory latches and how we can actually use what's called a holding circuit. So it's a really cool way to hook up the relay so it drives itself and it keeps itself on. Even though the signal that tells it to turn on disappears, the relay stays on. It's called a holding circuit. And we can actually multiply signals. So we'll get into that in a little bit, and I can show you that in some examples where one little switch can turn a lot of things on. It's pretty cool. Okay, good. So now, just the concept of adding a spring to something and the concept of a normal state. So I want to discuss this concept of a normal state. Anything with a normal state has a spring in it. And that's just, I need you to remember that. So if I say normally open or normally closed or normally anything, it means that that switch has a normal state. And that reason it has a normal state is because it's got a spring in it holding it there. So if I don't actively push the switch, or if whatever event makes the switch change its state, if that event is not there, then the switch is not going to change. It'll be in its normal state. Now, it can be normally closed or normally open. So we have these concepts here of these push buttons, and you're going to use these in the lab. So you have to get used to these. There are actually two different buttons here. They're not actually wired together in any way. So it just happens to be two buttons in the same box. So we have a contact here, and there's another contact on the other side, and there's one on this side, one on that side. So what's going on is that the start is normally open. The stop is normally closed. So what's going on is that when I press this button, it goes into its active state. It's no longer in its normal state. Its normal state is open. Therefore, its active state is closed. So when I press this button, the button becomes closed. And by the way, the button does not become normally closed. It just becomes closed. Because the name of the button is normally open. The state of the button can either be open or closed. So when I press it, it becomes closed. This button is normally closed. So when I press it, it becomes open. I hope that helps. I hope that makes sense. And that's terminology you're just going to have to get used to, and you will eventually wrap your head around it. So this is a good slide that you can always go back to. We must not confuse the name of a contact with its state. The name of a switch or a contact is either normally open or normally closed. The state of a switch or a contact is either open or closed. The normal state of a normally open contact is open. I think that makes sense. Okay? So when it becomes active, it becomes closed. It does not become normally closed. It simply is closed. Good. So the normal state of a normally closed contact is closed, because normally it's closed. So when it becomes active, it becomes open. It's not become a normally open contact. It's just simply open. So I think we're good with that, and you guys don't forget that. So now, with that said and done, before I get into the symbols and stuff, I really want to stop and pause and just see you guys and just say, okay, so what we've talked about so far is the concept of this whole thing about a relay. Talked about kind of a really good application for a relay. Different things we can do with a relay. We can control high voltages with low voltages and low voltage with high. Actually, you can do both. I can actually take high voltage and control low voltage if I wanted. So I can control two different voltages and two different currents. So I can have a low current controlling a high current. The cool thing about a relay is that I can reverse logic with the relay by using that normally closed contact. So I can say something like, if switch, then not light. Pretty cool. And then I have actually switches. That actually any switch, like a push button switch, any switch with a spring in it has a normal state. So I can actually say that if I don't touch a normally open, it's open. When I press it, it becomes closed. Yeah, cool. So one thing we did mention, that I did mention, was that I can, you can use a relay like as like a memory latch, or what we call the holding circuit, which we will talk about in Lab 4. So before I move on to ladder logic, or more specifically, how to put a relay into ladder logic, I'm going to have some tea and ask you if you've got any questions. No? How am I doing? Okay? Is this making sense? Yeah? Okay, good. That's awesome. That's all I need. I just need some, I need some interact, Can you repeat the question? What's the question? Yeah, okay, good. So I'm good. I'm glad we can move forward. Yeah, dude, it hurts me to be with you guys, but not be with you guys. Yeah, it sucks. Okay, so let's move on. So I know now that you know what I'm talking about, so let's move on. Here we go. So I press this button. How do I do that? What do I do? Share application. I'm going to press this button. Right. Okay. And we're going to go over the PowerPoint. And doom-da-doo-shka-doom-a-doom. All right, here we go. So now, this is kind of what we talked about before, and that's the coil, and this is the contact. Now let's put this into a ladder diagram. What's going on is that this circle here is not the relay. It's actually, I should label these CR, which means coiled relay, but I'm just calling it R1. So now in this case, this whole thing is a relay, but this little circle here is just the coil. So when I press this normally open start button, it becomes closed. This coil becomes energized. When this coil becomes energized, we know that this arm pulls down and my normally open contact becomes closed. This represents the contact here. So this symbol here represents what's going on here. So this thing and this thing are actually physically separate things. I mean, they're in the same box, but electrically, they're not connected to each other. They're only, you know what, wait, look at this. The only physical connection between this coil and that contact is a magnetic field. You can just think about it that way. Because, dude, this thing is just a coil, and we can see it here. This thing is just a contact, just like a switch, and we can see it here. So that's what's going on. So this is the symbol, this is the wiring diagram, and this is the ladder diagram. And there's actually logic here. Let's say this logic. If start, then light. I think that makes sense, because if I pressed the start, then the light would come on. So for logic statements, I break it down and I get rid of the grammar and I say if start, then light. I think that makes sense, nice and simple. Okay, let's move on and let's take a look at the normally closed contact, where we're actually going to reverse logic. So here we go. If I press this, then I know this becomes energized. When that energizes, the magnetic field makes this become closed, and when this becomes closed, the light comes on. So if start, then light. So we can say that pressing the normally open start button makes this energize, and then that closes this and the light comes on. Now watch this, this is cool. If start, then not light. But that actually means that the light's on, and it is. Because this, if I don't press this button, that is not energized. This is in its normal state. So its normal state is normally closed. Yeah, that's the symbol for a normally closed contact. So if I go back up here, this thing right here is represented by this wiring right here. That's the common, and that is the normally closed contact. So let me just see. I heard somebody say something, and that's cool. I just want to. Okay, yeah, man, Trippy's good. Okay, good. Yeah, okay, good. So yeah, if I hear you guys, you know what? I'm gonna turn my volume down. So, you know, if you really need me to stop and say no, Lars, don't do anything. Just actually turn your mic on and say, Lars, hey, stop. And then I will. So if I listen, I want you guys to talk amongst yourself while I'm doing this. So because, you know, you hear the little bloomp every time someone says something, but that's okay. So I'll ignore the bloops and you guys can talk, and that's fine. If you actually need me to stop, just holler. Okay, good. So that's what's going on. So yeah, it's pretty trippy, dude. It's really cool. So as soon as I press this, this goes into its active state and becomes open, and the light turns off. So if start, then not light. If start, not light. Yeah. Okay, cool. So now this is actual example when we're going to talk about like real life application, what's going on here. So this is kind of where we talk about the logic here. Okay, so the temperature switch is used to turn a heater on when it gets cold. I think that makes sense. So the contact of the temperature switch is normally open. Okay, so normally it's open. And it becomes closed when the temperature goes below, oh, that's interesting. It becomes closed when the temperature goes below 30 degrees Celsius. Okay, so what's going to happen here, if it goes below 30 degrees Celsius, this closes. Now, is there a problem? Follow the logic and you'll see an issue. Watch this. Okay, so let's say it's 20 degrees Celsius. So we know that the contact becomes closed when the temperature goes below 30. So 20 is below 30, so therefore the contact is closed. Oh, okay, so the heater's on. So if it's below 30 degrees, the heater will be on. Well, that's a problem. We want it to be the other way around. We want the heater to be on. Sorry, when it's below 30 degrees, okay, let me start this again. I think I don't know what I'm talking about, just momentarily, okay? When the temperature goes below 30 degrees, okay, then it becomes closed when the temperature goes below 30 degrees, right? So the heater comes on, follow logic. Okay, let's flip this around and we can reverse the logic. Temperature switch still normally open, but it's reversed with the relay. Okay, so the temperature goes below 30 degrees, the temperature switch will become open. What? Maybe I got this wrong. Just give me a second here. So, the temperature switch is normally open. It becomes closed when the temperature goes below 30 degrees. Oh, do you know what? I wrote this wrong, dude. You know what? Here, let me fix it. Watch this. Okay, cool. So, yeah. So, it's, okay, open. Okay, so the temperature switch is normally open and becomes closed. Oh, closed. When the temperature goes above. That's what I'm after. Okay, so let's do this. So a reversal logic temperature switch, but the signal reverses the signal. Okay, when the temperature goes below the temperature, the switch will open. And the relay coil is energized. When the temperature goes below this, it will open. Yes. Okay, this is better. Okay, so let's go here. Let's continue on here. I'll just do this. So here we go. So the contact of the temperature switch is normally open, okay, and it becomes closed when the temperature goes above 30 degrees. Okay, good. So this is the problem. So this will close when it goes above 30 degrees. Well, the problem is I want my heater to come on when it goes below 30 degrees because most temperature switches are like that. So they will close when they warm up, right? So the problem is, because this is going to close when it warms up, I want the heater to come on actually when this opens. Think about it. If the temperature goes below 30, I want my heater to come on. So there's a problem with the logic. So what I'm going to do is I'm going to flip it. And I'm going to take this and I'm going to put it onto a relay. So we know this becomes closed when it goes to 30 or above. So if it's 20, this will be open. That contact is open if it's 20 degrees Celsius. That means that that coil is not energized. This is in its normal state and the heater is on. If it gets to 30, this becomes closed, this energizes, this becomes open, and the heater turns off. So that's pretty cool. So what we're doing is we're reversing the logic of this contact with a normally closed. So we can say, if 30 degrees, then not heater. And we can also say, if not 30 degrees, then heater. Get this. If not 30 degrees, then heater. Because if this is not 30 degrees, that is not energized, and this is in its normal state, normally it's closed. So the heater will click on. So I can say, if 30 degrees, then not heater. And if I can say, if not 30 degrees, then heater. So that's cool. So yeah, no, there was a little bit of a bump there in the road because I used the wrong word over here. So, oh no, I'm jumping too fast. Okay, good. So there you go. That's a good example of reversing the logic. Now, I'm going to go even deeper here, and I'm going to say we're multiplying a signal, and we're going to reverse the logic. So in this case, I did explain to you earlier that one of the other things we can do with a relay is we can turn on more than one thing. We can have more than one contact. Let me just go up here a little bit more to here. Now, you see this is actually one contact. That's what we call the common. That's the normally closed, and that's the normally open. But you know what? It's just a mechanical thing that moves. I can put 2 of these, and 2 of these can be activated by the coil. Actually, I can put 4 of these. Some relays have 6. So I actually have 6 independent switches on a relay. So let me go back down to here again. And we'll look, this is an example here where we have one relay here. That should be R1-2. Okay, so that I gotta fix that. But pretend this says R1-2. Okay, good. So we've got one contact here, another contact, and another contact. They're all being activated by this magnetic field, by this coil. So there are actually 3 different switches inside this relay. I'm actually, there are probably 4, but we're only using 3 of them. So what we're now doing is we're controlling a heater, a motor, and a light with just one relay. So in this situation, what's going on is if the temperature is low, then the heater is on and the fan is not on. If the temperature is high, then the heater is not on and the fan is on. I think that makes sense. Now, I've added some logic down here, but we'll talk about that in a minute. For now, let's just take a look at what happens when the temperature is low. When the temperature is low, this is open. This is not energized. This normally closed contact is in its normal state. Therefore, it is closed. So therefore the heater is on. Okay, the temperature is low, heater's on. That makes sense. Now over here, this is not energized. So this R1-2 is not closed and the fan is not on. And that makes sense. Now what about this? Now that's a light. What's the light for? Okay, so if the temperature switch is both control, both, okay, additional logic is added to this rung. If the temperature is low, R1-3 will become closed and it's a capital and if switch 1 is closed, then L1 will be on. And L1 actually tells the operator that the temperature is low, but only if the operator wants it to tell him or her. So we've put a piece of extra piece of logic in here, and that what we're doing is we're putting a switch in here. So we can see that if the temperature is low, this will become it won't become anything. If the temperature is low, this will be in its normal state, therefore it will be closed. So the light will be on, but only if they press this button or they close this switch. So this switch tells the operator if it's low. Now, it could be that you don't want the light to be on all the time, because what if the machine is actually off? Whatever the machine is, we've just turned it off and it's off for the night. We don't need to run it all night long. So the operator comes along and he opens this switch. So the light's not on all night because the machine's cold. We've turned the machine off, right? So when you turn the machine off, you actually open this switch so that the light doesn't stay on all night, telling no one that the machine's cold. This light is just coming on for while it's running, and for some reason the heater stops, and then the operator can say, oh man, whoa, something's going on. The lights come on, let's check. But if, the operator's not there, he doesn't care, he's gonna turn this off. Now, I'm gonna sneeze. That was a good sneeze. So we've added some logic here, and thank you. And I can see here that it says if the temperature is low and the switch is closed, because these guys are in series, and we know an and is in series. Okay, so if it's low and the switch is on, the light is on. We're good with that. Now, what's this test thing all about? Well, imagine this, the operator in the morning, he wants to come along, or at any time during the process, he wants to come along and he wants to test to see if the light is working, because he may suspect actually that the temperature is low. He may say, geez, I think it's low. I think it's low. I don't know, right? But that light should be on, shouldn't it? So maybe the light's broken. Maybe, the actual fuse that's running the light, which is actually not here, or maybe the filament in the bulb is not working, so I'm just going to test it. And he tests it and he says, oh, the light is coming on. Okay, so my indicator that's really important to tell me if the temperature's low, it does actually work. So that's kind of a test to say, okay, it works. Now, the logic for this, watch this. The normally open test button allows the operator to check if the lamp is working okay. So if we take a look at this, we can take a look at, let's actually, no, I don't have the logic here. Let's say the logic here. So yeah, the logic for this rung is actually complicated enough that I can't say it because I need brackets, and we'll see how this complicated piece of logic can be said easily, but only if we write it down. So actually how it goes is bracket if not temp and switch or test. Wait, I bracket if not temp and switch, bracket or test. And we'll see that when we actually write it down. So let's take a look at this. This is a concept here that you guys know, that's an OR. And when we take a look at an OR in a ladder logic, it looks like this. You guys are experts at this. This is an AND. You're experts at this as well. This is a NOT. This is a whole new thing. So in this case, if not start, then light. Or we could say if start, then not light. Either way is proper. So it's kind of like A times B is the same as B times A. Okay, good. So let's continue on and take a look at the logic of that rung. So this is this ladder logic right here. We're going to unpack the logic statements of all of this. So this area here, we can say if not temp, then heater and not motor. Take a look at it. So if not temp, so therefore this is open. If not temp, then heater and not fan or not motor. That makes sense. And I could also reverse that to say if temp, then not heater and motor. Either or is perfectly acceptable. If temp, then not heater and motor. So that's good. Over here, this rung, just this rung right here, just that rung, the logic of that is if not temp, because this means not temp. If not temp and switch, then light. Now, this is where we add some logic here. That logic is in a bracket. So this piece of logic is being bracketed with this piece of logic in an OR. So this or this, these things or this. And the way we say that is if not temp and switch in brackets or test, then light. I think that makes sense. So we're talking about some pretty cool stuff here about, you know, how to actually say logical statements and actually put them into a ladder diagram, because often when you're designing stuff, you're kind of thinking, okay, so I need it so that if the temperature goes up, heater comes on. And if somebody opens the door, but if the temperature is low, then the heater should come on. But if someone opens the door and the temperature is high, then the heater shouldn't come on. Something like that. So now get this. This is a pretty cool example here. Let me just kind of walk through this with you guys. Now this is this is a little trippy in itself. Okay. What's the logic here? So, or more specifically, if the button is not pressed, is the lamp on or off? Okay. So if I don't press this button, that is not energized, that is open, so therefore the lamp is off. Okay. So if I don't press this, the lamp is off. What if I don't press that? What's the lamp doing? Well, I think you guys understand. If I don't press this, that's not energized. That's in its normal state. It's a normally closed contact. So it's closed. So the light's on. So if I don't press this, the light is on. Okay, now wait a second. What about this? If I don't press this, is the light on or off? Any thoughts? I'm going to go over and I'm going to see what you guys have to say. It's on. It's on. You're right. So if I don't press this, let me just expand this a little bit more. Oh, no, excuse me. Can I? Thank you. Yeah, you're right. So if I don't press this, it's a normally closed contact, so, or switch. So it's closed, so this is energized actually, and that becomes active, so it becomes closed, and the light comes on. Okay, now this one. If I don't press this, is the light on or off? Really? You guys don't know? Okay, think about it. I don't press this. It's a normally closed contact, so it's in its normal state. So this is now going to be energized. If that's energized, this is in its active state. Because it's normally closed, it becomes open and the light's off. Oh no. yeah, on, off. Let's go over this again. Okay, dude, every single time I do any kind of ladder logic, I always say to myself, okay, I want to see what happens to the logic if I don't touch anything. Okay, so in this case, we're not going to touch anything. Okay, this switch is closed. So therefore, this is energized. If that's energized, this is not in its normal state. It's in its active state. A normally closed contact in its active state becomes open. So this light will be off because this is open. So there you go. So that was a nice little exercise, and I thought it would be kind of fun to wrap our head around how that logic works. So you can see, how it can get a little bit deep. And this is just simple. Imagine what it's like when these ladder logics get really complicated. It gets out of control. So it's a matter of practice to wrap your head around this. Okay, so let's talk about inputs and outputs and what they are in a ladder logic. But before I do that, I think I'm just going to say, does anyone, yeah man, it's time to study up. So does anyone have any questions before I go on? So what we just did was, we just talked about this whole thing about logic itself and what it looks like here. So what I want to do now is I want to get into actual contacts and what they look like, what these input things look like, and then what output looks like, and then I'm going to define what events are. So I'm just going to roll with this. If anyone's got anything, give me a shout out. Okay, good. So now let's go here. Let's do this. Okay, here we go. So inputs. They tell the control circuit what's going on, right? Just what's happening in the environment. Inputs come from switches and sensors. So an input comes from a switch or a sensor. That's it. It really doesn't come from anywhere else. Inputs come from switches or sensors. Inputs can tell the control system about conditions such as temperature, pressure, liquid level, proximity, operator feedback, like a button. Yeah, a button is an input. It tells all of these things, tell the control device about events. Let me tell you about what an event is. So signals and events. Events are really complicated. It's really hard to wrap your head around an event. I mean, it's really difficult. Okay, here we go. Inputs give electrical impulses called signals to a control circuit. Okay, so any kind of input is going to give some kind of electrical impulse. Okay, that makes sense. Events are simply things that happen. Events are translated into electrical impulses or signals with a switch or a sensor. So I will go over some events. An event, let me just, I actually want to do this. Okay, you guys need to see me. Okay, wait, that's good there, and that's good. Okay, good. So now let's go over this. I need you to understand the difference between events and electrical impulses and signals. Okay, an event is translated into an electrical impulse through a switch or a sensor. That's actually one of those heavy, profound statements. I'm going to say it again. An event is translated into an electrical impulse with a switch or a sensor. Then a circuit can use it. So I'll give you an example of an event. An event is Buddy presses the button. An event. Someone presses a button. Okay. Another event is someone walks through a door. Another event is the liquid level goes above a set point. Another event is the temperature goes below a set point. The pressure goes above or below a set point. Something moves. Something opens. Something closes. Something happens. So, in all of those cases of events, not once did I talk about any electrical impulse. Not once did I talk about an electrical device except for one time where I said an operator presses a button. So, I need you to start thinking what I call event programming. When you're programming in your ladder logic, which you will be doing, you'll actually be programming ladder logic, because ladder logic is a programming language. But not only is it a programming language, but it's a wiring diagram. Yeah, it's so cool. So, with that said, I need you to think about the events without the electrical impulses, without the switches, without the proximity sensor, without the pressure switch, without the whatever. Just think about what happens. Okay, so when this thing starts to spin faster than 75 RPM, then a light should come on. Okay, what's the event? Well, that thing started moving faster than 75 RPM. So we could say, when the encoder gets a signal that the motor is moving more than 75 RPM, then the electrical impulse is going to turn the motor on. No, dude, the event has nothing to do with the encoder or the sensor or any switches or it's just something that happens. Okay, so an event is translated into an electrical impulse through a switch or a sensor. Yeah, I'll say that a lot more. I need you guys to say that in your head. So here we go. So let's go back over to sharing the screen, and then we'll continue on with this whole event and electrical impulse thing, and actually put it into application where we can see some of these things that are actually making sense, and we're actually going to do some programming. So here we go. So these are all events, right? So temperature, pressure, liquid level, proximity, operator feedback, these are actually just events, things that happen. But you know what? We use the electrical impulses, or we use the switches or sensors to give us that electrical impulse. And these are all kinds of switches or sensors. So a signal comes from a switch or a sensor. So what's going on is this is a switch. These are all actually switches here. In ladder logic, we actually only use switches. We don't use sensors, and that's a whole other thing that you'll learn in mechatronics. Okay, here we go. So this is a normally closed temperature. So when the temperature goes above a certain amount, it becomes open. So that's a little bit different. That's a liquid level switch. We can have a normally open or normally closed liquid level switch. This is a pressure switch. We can have a normally open and a normally closed. We can have a float switch, normally open, normally closed. We can have a timer contact, normally open, normally closed. Now, I've added timer contacts in here because I believe that a timer contact translates an event into an electrical impulse. The event is the time has been reached. So timers are a little bit more complicated. They're electrical components, but yeah, again, a timer contact is just translating an electrical signal that comes from an event, and the event is the time's up. A limit switch indicating that something has reached its limit, like a door has been opened all the way, or a door has been closed all the way. And obviously a float switch is going to be floating up and down. A pressure switch is going to tell you if the pressure is reached a certain level. So all of these switches we will learn more about as we put them into ladder logic. Okay, here we go. So now, control example. A water reservoir has a monitoring system that will turn on a motor opening the water gate if the level goes above a set level, or if an operator closes a switch. Now, the first word that jumps out at me here is the word or. It's actually really important. This is probably the most important word in this sentence for a programmer. Yes, we are programmers right now. We're designing a circuit that actually has a logical decision-making ability to it. We need this or in here. So, okay, the water level has a monitoring system that will turn on a motor, okay, in ways if, that's the other most important word. If the level goes above a set, or if an operator, then the motor comes on. Okay, so this motor is going to come on if an operator closes a switch or if the water goes above. So I can make a statement. If the operator closes a switch, the motor will come on. If the water goes above a certain spot, then the motor will come on. So I'm going to put those together in an or because I know an or is here. So if water or switch, then motor. Cool. There you go. So and then there's a manual override that an operator can use to the gate. So that's the switch here. So what we're going to do is we're going to define the events, and then we're going to choose the inputs. We're going to choose the outputs actually, because in any control, we're actually controlling something. In this case, we're just controlling a motor. But we have to define the events. And I think in this case, the events are pretty simple. We're going to choose the inputs. We already kind of know one of the inputs. There's obviously going to be some kind of input that tells us about this water, the water level. So it's probably going to be a float switch of some type. and then we'll continue on. So we're going to write the ladder logic, we're going to write the logic statements, and then we're going to build the ladder. It's that simple. So you don't have to like do these step by step. I mean, this you just do in your head, and these you just kind of choose them in your head. So let's go here. Let's define the event. So the event here is pretty simple. An event is translated into an electrical impulse from a switch or a sensor. Okay, so what's going on? Events have nothing to do with sensors or electrical components. An event is something that happens. It's that simple. A door opens. We talked about these. The event in this case is the liquid level example. The event in this liquid level example is, the event is the water goes above a set water level. Okay, here we go. That's it. The water goes above a set water level. Okay, that's it. So in this case, we're going to continue on here and we're going to say, choose the inputs. Okay, so how am I going to, what input am I going to use to tell me the water level's gone up? I'm going to use the liquid level switch. And that's what that looks like. So in this case, I have to think about whether I want a normally open or a normally closed. Okay, so I have to think about this. Inputs are signal, impulse. Yeah, okay, it's ladder logics. Switches are used as inputs. Most switches used in ladder logic are either normally open or normally closed. Okay. When a normally open switch is activated, it becomes closed. When a normally closed switch is activated, it becomes open. That's something I've been shoving down your throat over and over and over again, but I've had so many years where students have said, well, the normally open switch becomes a normally closed switch when you press it. Yeah, and then I get upset. Okay, here we go. The switches in this liquid level example are a normally open level switch. Cool. I mean, I could use a normally closed level switch there, but I'd have to reverse the logic with a relay. So I'd probably actually end up with two relays in a circuit. I only need one. So I'm just going to go buy a liquid level switch that becomes closed when the liquid level gets to a certain point. Okay, good. And you know, it's a matter of where I place this liquid level is where the actual liquid level or the set point is going to be. It's a matter of where I actually physically put this switch. Now, the other switch is going to be a simple single pole, single throw switch. I flip it and it becomes closed. So when the liquid goes above the normally open level switch, it becomes closed. Okay. Oh, becomes closed becomes. Oh, I got a little special with the word becomes there. So here we go. Now, what we're going to do is we're going to define the outputs and we're going to kind of start to build the ladder. So let's take a look at this. My output is going to be a heater. So I can just simply draw this on the right-hand side. Okay, good. So I'm assuming that I'm going to put this in here. And we'll talk about that in a minute, but let's just ignore this for a second. And let's actually take a look at all of this. So these are just examples here. So I can take a look at this logic, and I've just put all of this here as an example. It's not the liquid level, obviously, because that is a pressure switch. That's a temperature switch, and this is a timer. So just talking about this piece of logic here, I can say this comes from a relay, okay? These are in an OR, but it is ANDed with this, and that is ANDed with this OR. So the way we say this logic is difficult. We write it down. If this contact, if R1-2, okay, and pressure or T1, and with a bracket and temp 22, which means the temperature has reached 22 degrees Celsius, then the heater. Okay, cool. So that's just an example. So let's take a look at this, but just say about the outputs. I want to talk about outputs. Outputs are things that come on, motors, heaters, buzzers, lamps, anything just that goes on. Anything we're trying to make go is an output. Okay, good. So if we take a look at this, logic statement is used with words, and we don't use full grammar. They're not really sentences. They describe a logical progression as simple as possible. They're more like programming code. And I think some of you guys have done some programming before where the logic of the programming is there's no grammar. It just boils down to really simple words like if or and or not. And the word then. We'll always have an if and we'll have a then, because if a certain something with an and, an or, a not, then this. This can get really complicated, but it's okay because It's all about the geometry of how we put it together. So if I had some really crazy complicated statement here, I could just make it geometrically complicated and it would be okay. Okay, cool. So in the logic statement, which is in this whole liquid level statement is this. If level switch or switch one, then motor. It makes sense. I mean, the original statement going up here, okay, so here we go. So this is the if the level goes above or an operator closes the switch, then this motor comes on, and it's really simple. So we've unpacked the inputs, we've unpacked the outputs. We understand that outputs can be all the kinds of things. We understand that the logic can be really complicated, but in this case, it's as simple as if level switch or switch one, then motor. So we know that we can just put them together in an OR, which is parallel, and then we can just do this. Now, let me just talk about this. I'm going to jump back to the ladder in a minute. So this is the logic here. So brackets, right. So brackets, we talked about logic. Where's the, so this is the logic here, dude. I'm going to go back to those other slides, but I'm just saying in this example, we can say if level switch or the switch, then the motor comes on. It's that simple. Okay, good. And you know what? If the motor comes on and opens a gate, then when the gate opens, the water level is going to go down, and eventually this switch is going to become open. The motor is going to come off, and I'm assuming the gate works on gravity or there's a spring or something, and it will the gate will go up again or will become closed, or it'll go back to its normal state, which is blocking the water. But we really should put an on-off control. And the reason I'm talking about this is we're discussing how to design ladder logic, logical statements. In this case, we know the statement is if liquid level or switch, then motor. But we really should add a little bit more, not control, but power. Like, we actually should put some safety in here, and we should say, dude, I want to be able to turn this whole system off, especially if I want to go over to maintain it or do something to it. I want to be able to turn the whole thing off. So when we put an on-off switch in here, we're not actually adding any logic to the statement. I mean, you could say if on or switch or level or switch, then motor, but we don't add this on and off to the actual logic. So going back up to here, I want to discuss what a ladder really is. You guys have got an idea about what a ladder is in Lab 2, but essentially a ladder has these rails on the right and the left, and it's made up of rungs like a ladder, where each rung has a specific logic that becomes active when that logic is satisfied. Now this is important. I need you guys to hook up your circuits like the geometry. I've mentioned this in my videos. The geometry of a ladder logic is governed by its logic, the shapes and the way we put things together. So if you know the statement for the control logic, you know what? The ladder is really straightforward. You can just put it together using the geometry with ORs, ANDs, or NOTs. It's that simple. ORs require inputs in series, and you know that. ANDs require inputs in parallel. NOTs require a relay and a normally closed contact. The brackets in a logical statement group inputs into something kind of like subroutines and allow two or more inputs to OR and to AND or to NOT. So I think that makes sense. And I've gone over that with examples where we looked at these examples here, where this is this and this are ANDed together. So you guys get that. It's just a matter of this, like, you understand what I'm talking about. It's just a matter of getting this into your head and practicing it. So let's take a look at two sentences that are said exactly the same, but I've put the brackets in different places. So take a look at this. Bracket, pressure or T1-1 and temperature 22. So that means this is ANDed with this. Now in this situation, what I've got is I've moved the brackets and I've moved some things around a little bit. So I've got pressure T1 and temperature or not. You know what? Here, let me go here. Okay, so that's just better. Here we go. So if pressure and temperature 22 or this, then. So we can see what's going on here is that this is all configured differently. What I did was I took this line and I put it over here, which means that these guys are now an and that and is ORed with this. So I hope that makes sense. I'm sure it does, and you guys are getting, this is not complicated concepts, but it's a matter of you practicing this to get it into your head. Okay, good. So now we're actually going to talk about the actual physical lab itself, but I want to talk to you about, I'm going to introduce you to the actual relay itself. Okay, using a relay. Each relay in the Humber lab has 4 individual contacts. So what's going on here is this is the contact. We know that's the normally closed because there's a spring pulling it up. Somewhere down here is a coil that's going to pull this down here, and it's going to connect to the normally open. So there are actually 4 of these. Each one of these has a common, a normally open, a normally closed, and a normally open. Each has a common, a normally open, and a normally closed. This is another one of the contacts. It has a common, a normally open, and a normally closed. Common, normally open, normally closed. Common, normally open, normally closed. So there are actually 4 physical contacts in here. When this coil energizes, all of these contacts change their state. So this connection is no longer connected to the normally open when this changes its state. This is connected to the normally closed. It's connected to the normally open. I'll say that again. When this is energized, this whole relay changes its state. Each one of these contacts changes its state. This contact is no longer, if this common is no longer connected to the normally closed, because it's not in its normal state, it is now connected to the normally open because it's in its active state. And in its active state, the normally open becomes closed. Again, it's just a matter of practicing this and actually going over and over the actual diagrams and building these diagrams yourself and saying the logic in your head. In this actual, even in last week, I told you to, for lab 2, I told you to say the logic out loud in your head. Okay, good. Now, what's going on here is that I have this relay box. In this relay is a coil and a bunch of contacts. In a ladder diagram, the coil is represented by this. This is one of the 4 contacts. The left side is the common. The right side is the normally closed. So in this case, this orange part is this guy right here. It's the common. So the left side is the common. The right side is the normally closed. And the reason it's normally closed is because it's this symbol. It's not this symbol over here. So if I were to hook this ladder logic up with an actual circuit, it would look like this. I would have my power supply, which are the rails, the positive side and the negative side. And I've got my positive, and my positive seems to go to the left side of the start. So there's a wire that goes to the left side of the start. Out of the right side of the start, out of the right side of the start, into the left side of the coil, into the left side of the coil. And by the way, the bottom is the coil. Out of the right side of the coil to negative. Out of the right side of the coil to negative. Sweet. My next rung. Always build one rung and then build the next rung. My next rung, there is power coming out of the power supply and going to the common of this contact. And you can see the power line is coming out of here and it's going to the common. And that's that orange bit there. And you can see the orange bit there. It's the common. Now, out of the normally closed, I'm going to go to the left side of the light. Out of the normally closed, I'm going to go to the left side of the light, out of the right side of the light there. So you will have seen and heard me say left side, right side many times. And the reason I'm saying left side, right side is because the ladder logic, even the first ladder logic is confusing when you're using the relay. You have to think left and right. You have to think the left side of a contact is the common. The right side of the contact is either the normally open or the normally closed. The left side of the light, the right side of the light. Because when you're physically wiring things and you're looking at the diagram, it can get pretty crazy. It can get hairy. You're like, okay, this goes to the light, but no, it goes to 2 places. You go crazy. So yeah, I need you to kind of be consistent in your wiring of all of the diagrams and the left side and the right side. Now, I'm going to then talk about the actual lab experience you have, but before I do that, I'm going to have some tea. And just ask you guys if there's anything that you want to pause and stop and study and just questions, you can have your tea too. I'm having green tea. It's probably cold. Nobody said anything, so I'm going to get right to it. I'm going to tell you what the lab experience is going to be like, and then I will field any technical questions, and then I will let you guys go, and then I will go, and I wish you a very Merry Thanksgiving. But I won't do that yet because we're not done. Okay, good. So here we go. So let's jump into the actual lab, and I will show you what's going on in the lab. So I'm going to go over to Blackboard. All right, rock and roll. So let's go over to Blackboard. We're in Blackboard. Let me just, you know what? We're all in Group A. Even Group B has got the same information in it. So in Group A, I'm going to go into Lab 3 because we're doing Lab 3. Now we've got two things going on here. One is this PDF that we just went through, and you have access to that. The other is the physical lab itself. So I'm just going to click on here because I've already got the lab open here. So let me zoom in a little bit. So this lab is called Relay Control. I should actually call it Lab 3 ATMN 110 Relay Control. Okay, good. So now that we know Relay Control, we're going to learn all these things. And I'm actually going to add more stuff to this. So by the time you go into school on Tuesday, there's actually going to be more questions in here, but they'll not be that complicated. Okay, good. So go to the lab, get one of these, one relay, a motor, and a light, and it seems that they're already on the desks. Pardon me, you need two lights. One light we're going to simulate as a heater. Okay, here we go. And now you're going to go in there and you're going to hook up. This is really complicated circuit, dude. I mean, it's really complicated. You've already done this. It's good. So the reason you're doing this is, in this case, you're not turning on a light anymore. You're turning on a relay coil. Yeah, you're turning on a relay coil. And then you're going to test the continuity of the relay coil. So we know that there are 4 switches inside this relay coil. Each of those switches looks like this. We can see if I do not energize the switch, there is no connection between the common and the normally open. So what's going to happen is that your continuity meter will not beep because there's no continuity between these. And as soon as you close this, this will energize. This armature will come down. This arm will come down and go to your normally open. The normally open will become closed, and then you're getting continuity between here and here. So it's pretty simple. You're just going to put open or closed. You're going to write the word open, or you're going to write the word close. Open, close, open, close. So, that should be a normally, yeah. For this contact, you're going to test the normally open and the normally closed while it's energized and when it's not energized. And the reason I'm doing not energized and energized is because I really need you guys to get used to the word energized, because we don't turn coils on, we energize coils. Cool. So let's move that. Excuse me. I want to move that. No. Move you over here. Okay, good. So now let's move that over there. I can move that there. Okay, good. So let's move down over to here. So that's the one. And then you're going to do the exact same thing for this contact, because I need you to get practice understanding that that's the common, that's normally open, and that's normally closed. So there you go. So those questions there. Now you're going to hook this up and you're going to get a signature. So what's going to happen here, if we look at this logic, we've talked it already. So I'm putting a normally open push button here. So I can say if push button, then heater and not motor. I can also say if not push button, then not heater and motor. So you're going to hook this up, you can press a button, and you'll notice the heater comes on and the motor turns off. So you know what the heater is, you know what the motor is, it's the motor. The light is going to be the heater. So you're going to simulate the heater with a light. I think that makes a lot of sense. And then you're going to answer some questions here. Each one of those, that's the common, that's the common, that's the common, that's the common of the 4. How many commons are used in this circuit? How many commons are used to here? I need you to understand that there are 2 commons, one here and one here, because this contact is entirely a different contact than that contact. It's actually 4 commons. Okay, good. So because some students, they put a wire going into here and then they run 2 wires out of here and out of here. By the way, you can only use the normally open or the normally closed. I don't want you guys using both of these, not yet. I mean, we can get into that later, but maybe even in a whole other course. That's complicated stuff, dude. When you use both of these and you get some feedback and stuff in your circuit, it's not a good idea. only use either this contact, either the normally open or the normally closed. Don't use both. Okay, good. So these are simple questions. And here's a logic statement here, and then you got to guess which one it is. Now you got to build this, and all you're doing is you're putting an or an override in here. So it's the exact same circuit. Look at this. This circuit is the exact same circuit as this circuit, except you're putting an override. And now you have to actually say the statement for the override. Should be, if. Okay, start with if. And then you have to actually write that down. So there's actually a question here where you actually have to enter the logic statement for this rung. So I'm going to actually add a couple more circuits in here that are pretty simple, but they're just not there right now because I haven't actually built them yet. So hold on a second. Let me go here, camera, and there you go, and there you go, share camera. So that's what's going on. You guys are experts at this. Now I'm going to tell you something really cool. I'm actually going to, you know what? I'm just going to jump into where I want to go. Your application. Now we're going to go to Blackboard. If you guys want to jump ahead, that's a great idea. Watch this video. You know what? Everything I just talked about, I talk about again here, but more practically in what's going on.
So let's unpack relays. Relays are pretty cool little things. They're almost like kind of remote control things in that moving the switch for you. So what's going on here is that I'm like open. I need you
So that's a great video. This is a good video because I'm discussing, you know, more of the logic of the ladder logic. And I've got, you know, you can see that circuit that I put on the board is a little bit more complicated. And I'm getting into some solenoids and stuff. Where's my solenoid? Oh, there's no actual solenoid in there. Anyway, so that's just a discussion. Now watch this. I am going to jump into lab. You guys can go here too. It's a video series on ladder logic. So, dude, go down here. If you want to get ahead on this stuff, go down here. And I did a lot of stuff here. So this is discuss how a holding circuit works. So next lab, we're going to do a holding circuit, which is amazing. Like, dude, when I learned what a holding circuit was, it was transformative for me. I'm not kidding. Like it was, I actually remember the moment. I'm going to have a moment with you guys. When I tell you about what a holding circuit is, I'm going to tell you the story of the moment I had. It was transformative, like in my life, what a holding circuit was. 2 holding circuits. Okay, cool. And control a tank and all that. And then there's more, dude. Wow, this keeps going. And then there's timers. Well, that's amazing. There are a lot of resources in there. So I strongly suggest you guys, if you really want to get ahead, if you're really hungry for more knowledge, just watch all those videos. They're there. And I will do more as well. So those will be really helpful for you to wrap your head around ladder logic. Because you're going to have to design your own ladder logic for the exam, and also for lab 6, you're going to have to design your own ladder logic, and or lab 5, I'm not sure. But yeah, because I'm actually rewriting all of these labs because COVID just hit us and I had to redesign all the labs. So I'm not actually sure what the labs are going to look like. I know all the learning outcomes, and I'm not sure where I'm going to fit them all. So with that said and done, I think we're good. And I'm just going to say, sorry, oh wow, okay, Tuesday class, sort of example. Yeah, so I will jump on that question in a moment, but I think I'm just gonna say goodbye to everybody on the recording. Yeah, we'll see you next time, and happy Thanksgiving.